Hello everyone. Today I will present the paper DeepSeek-OCR context optical compression by the original authors. My goal is to explain what's the problem they study, how their system works, what they report in training and evaluation, and what's conclusion and future direction. The second, I will um, explain this motivation. The motivation in this paper is very simple. Long contexts are expensive for large language models because cost scale with the number of the text tokens. The authors propose alternative paths don't carry context as text tokens. Instead, render page as images compress every page into a small number of the VSON tokens and decode back to text and structure when they needed. This evaluation OCR setting because it has the rich layouts and clear metrics like edit distance and accuracy. The practical target they emphasize is roughly 7 to 10 times compression with staying close to lossless, keeping activation small and maintaining high throughput outputs. On the third slide, I will emphasize their novelties. This paper novelties can be concluded four parts. The first, they propose a high resolution encode. This encoder can keep the activation small. They use the local processing first and postpone global attention until after having done something. The second, they propose a mixture of XPerf decoder around the 3 binary parameters class, where only a subset of the XPerf is active per token. So you can get the capacity without paying full compute each step. The third novelty, they propose multi-resolution operations. It can support multi-resolution operators. For example, they have fixed native modes. It includes tiny, small, base, large, and also have dynamic tuning modes called Gundam. They can join the local tails with global view for the dense page. The last contributions is that they propose explicit compression accuracy curve. Under this curve, we can get how to control the buckets tokens. For example, if the ratio compression is less than 10 times, text to the vision token the OCR precision is around 97%. Push near 20 times drops it to roughly 60%. Uh, the next, I will introduce the whole framework of the DeepSeek OCR with the architectures. We can see it can be include two parts. The first part is a deep encoder, and the second part is a decoder. The authors use unified end-to-end vision language model. We first look at the first encoder. It's called deep encoder. It can turn each document page into a complex sequence of the image tokens. And then they will use the decoder read these tokens and also they will plus some prompts. This prompts come from the users and they will use this MOE to generate the final outputs. For the encoder, his it's about 380 million parameters in totals. It can include two well-known backbone in series. The first part is the SAM. This it's include 300 million parameters. Sorry, it's 80 million parameters. And then the second is the clip. This is includes 300 million parameters, and between them is two layers convolutions. He will downsample the inputs to 18 times. And this decoder is MOE architectures. It will have 570 million activating parameters during inference. The key idea of MOE here is routing. Only a small subset of experts is activate for each generated tokens. It will keep the compute practical while preserving capacity. The decoder consumes the image tokens from the deep encoder. And the prompt the user provided. Okay. And we can see this end-to-end flow. The pipeline is as follows. The first, the user input the page images, and we will develop this input into different patches, and this patch will go through this deep encoder, and then we got the image tokens and send these image tokens to the DeepSeek decoder, and plus the prompt, we will get the output. This part is about the deep encoder architectures I described in last slides. Here I want to emphasize that this have 5 design goals. For example, the first is capable for processing high resolutions, low activation as a high resolutions, few within tokens, supports for multiple resolution inputs, moderate parameter counts, and this is detailed. This is detailed. Okay, and this part we will introduce he supports multi-resolution modes. For the small, he can be 2 patterns. The first pattern is fixed resolutions. For example, he will reset the output document into the fixed page. It can be include 4 patterns. For example, tiny, small, base, large. For the tiny, his input is 512. For the small is 640. It look like this, and he will use fixed tokens. For example, if you use the tiny mode, you will use 64 tokens to represent the input informations. And they also have dynamic resolutions. That means you can support dynamic inputs. For example, for this, they call this pattern as Gundam patterns. His resolution is 600 at 1022. And we can see his tokens is dynamic. He has a formula to calculate that. This N is donate the tail. It looks like this picture. For this for the third page, we can see his his document can be divided for 6 parts. This represent 6. It look like this. This is for the dense input. For example, for the newspapers, he have a lot of text and contents. And the last part is his decoder. We can see his decoder part is based on MOE architectures. It look like this. His goal is to reconstruct the input text and his layouts. So he can not only support text, it can also generate markdown tables look like this. This part is about his data and training part. His data include these 4 parts. The first part is OCR 10 is a classical sense and documents OCR. The OCR 2 points is a synthetic structures charts or chemistry. Is look like is specific data for the domains. The third data is the generative vision, caption, detection, grounding to keep the vision interface. They also include some text-only data, and we can see his training data is include 70% OCR data, 20% generates vision, and 10% text data. And his training can be divided for 2 steps. The first step, they will train the deep encoder first. And this goal is to got very complex token representations. And the second training is to train the full architectures. For this training, it can be divided to 2 steps, and he will use the pipeline parallelism techniques to achieve this training. And they also report his hardware configurations. For example, he will use 20 nodes times 8 times A100. Each 100 have the 40 gigabytes, and his batch size, is 640. We can see his results. He evaluates their results in 2 well-known data for data sets. We can see the first benchmark. We can see if the for the first one, his compression ratio is about 10 times. It can be achieved 98.5% results. The second figure is the text on the OMI doc bench. If the edit distance is are smaller, the results are better. So we can see, for example, these are better if it's only use it's hundreds tokens. It can be a very good results. We can say it's better than GOT OCR 2 points. Even they use this 100 token 100 tokens, his results is better than this GOT OCR 2 points. And this DeepSeek-OCR, this Gundam patterns is better than this compared results. This figure also can show if the compression ratio is less than 10, we can see his accuracy is very good. It's near achieves 96.5%. But if the compression ratio is 20, nearby 20. We can see his compression, his OCR precision will drop to 60%. So from this paper, we can got these conclusions. And we can also do some very interest in the future direction. For example, we can do some adaptive resolution and token budgeting, handwriting, math, chemistry, and diagram extension. And we can also do some data entry and reproduce the training recipes. Okay. Um,